Section 5.3 is on the sum and difference identities. Just a little heads up to you that the sum and difference identities may also be known as the addition and subtraction identities. So you will see that referenced in both ways as we move through section 5.3. In section 5.3, when we talk about the sum and difference, what we're looking at is when we have the sign of two things added together. And what we want to make note of is that the sign itself, just SIN or the sign function, isn't a number. And so since it's not a number or a constant, that constant can't be distributed into this set of parentheses. So the sign of x plus y is definitely not the same as the sign of x plus the sign of y. I cannot distribute the sign since the sign is not a constant. You could try graphing it on your calculator. Graph something like the sign of x plus 30 in y1, and then in y2 distribute that sign, which again is not possible to do. But if we do this as the sign of x plus the sign of 30, you would see that the graphs of those two functions are not the same. We also could check that out on our calculator. So I have an example typed out here, and then you can see the answers my calculator gave me. If I have the sign of 90, I know the sign of 90 is 1. I could say that 90 degrees is the same as 30 plus 60. And so if I typed in the sign of 30 plus 60, as you see here, I also get 1. But if I try to distribute the sign through and type in the sign of 60 plus the sign of 30, as you see here, it is not equal to the same thing that we had when we were adding the 60 and the 30 inside the parentheses. So moral of the story, distribution does not work unless you're distributing a constant. And so we need another method to be able to simplify these expressions. So we're going to look at the addition and subtraction identities. These are listed on page 437. They'll give you an idea of where they came from if you want a little bit of background information. And so you're seeing some identities listed here for the sine and for the cosine. You may want to write these on your green sheet on the back side. You have room to be able to write these. The first one, sine of x plus y, is the sine of x cosine of y plus the cosine of x times the sine of y. When we have subtraction between the angles, the only thing that changes in our expansion here is the sine of x times the cosine of y minus the cosine of x times the sine of y. If I was writing this on my green sheet, I would list all of these under option number 1, and you can write the x and the y with a plus or minus, and then that just gives me sine of x, cosine of y, plus or minus cosine of x, sine of y. We're going to see our second identity with the cosines. Cosine of x plus y is cosine x cosine y minus sine x sine y. When I have cosine of x minus y, now it's cosine x cosine y plus sine x sine y. And how we would write that on the back of our green sheet for option number 2 is the cosine of x plus or minus y equals cosine x cosine y, and we're actually going to write minus or plus. You probably haven't written that before, sine x sine y to end this. And so usually people haven't written the minus or plus. Sometimes people say, does it make a difference? It actually does, because the sign and the top, when it's plus inside the parentheses here, then we're using the minus over here on the right side. When it's minus inside the parenthesis of the x minus y, then it changes to plus in the expanded version here. So these are our addition and subtraction identities, or sum and difference, for your sine and cosine identities here. We'll get to the tangent in just a little bit, and these are going to be helpful to find the exact values of angles when we don't have a special triangle like a 30, 60, 90 that we can draw. So let's look at a couple examples of how that's going to work. I have the identity up in the upper right hand corner here for us to use. Find the exact value of the cosine of pi over 12. Now, some people aren't quite as comfortable working in radians, so it might help you to start out with by saying, changing that radian measure to degrees. So pi over 12, 180 over 12, it's going to give me a 15-degree angle. Now, 15 degrees doesn't come from one of our special triangles, so what we're going to do instead is we're going to think, can I rewrite 15 degrees as a sum or difference of one of our angles from those special triangles, a 30, 60, 90, a 45 or a 90, or anything with a nice reference angle. So 120, 150, 225, anything at all that has a nice reference angle from one of our special triangles. So the cosine of 15, one option I would have is to use a 45-degree angle and a 30-degree angle. But remember that there's more than one choice that's going to get us to 15 degrees. So another option just off to the side, I'm going to leave this one here because that's the one I'm going to use as I expand it. But I also could have picked the cosine of 60 minus 45 and used my identity that way. I could also pick something from a different quadrant. Maybe I pick the cosine of 135 degrees minus 120 degrees, and I use the quadrant 2 angle. Both of those subtract inside the parentheses to give me 15 degrees, and both of them would give me an accurate answer in the end. All right, so let's use what we have here in red to expand using the formula. And so as I do that, I have cosine of 2 angles subtracted. So I'm actually going to use the bottom version here, right, with the cosine of x minus y, and then fill in there. So that means if I expand it, I get the cosine of 45 degrees times the cosine of 30 degrees plus the sine of 45 times the sine of 30 degrees. So what I have in purple there is the expanded version. Again, I don't have to worry about this as a negative 30. It's just subtraction, and the formula takes care of itself. Again, go back to your textbook. They'll have an explanation in there as to where that comes from if you're curious. Now we're going to evaluate the cosine of 45, cosine of 30, sine of 45, sine of 30. What you're likely going to do is, number one, probably on your green sheet, you already have these special triangles drawn. If you don't, you can either draw them on your green sheet, or maybe you'll choose to just draw them in your notes or in your homework so that you can reference these triangles without having to redraw them every single time. So I can draw, I'm going to redraw this triangle here. I can draw a 45, 45, 90, and I can also draw a 30, 60, 90 triangle. There's going to be my 30 degrees, 1, square root of 3, and a 2. So I'm just going to draw them so that they're off on the side for me, and I'm going to use them to evaluate. What's the cosine of 45? Cosine is adjacent over hypotenuse, so I have 1 over square root of 2. We had mentioned earlier that it's much easier to simplify if we actually write the rationalized version of that. So I'm going to write cosine of 45 as square root of 2 over 2. Remember, 1 over square root of 2. If I rationalize, meaning I multiply the top and the bottom, whoops, I meant a 2 down there. If I multiply the top and the bottom by the square root of 2, that's equivalent to square root of 2 over 2. So we could keep the 1 over square root of 2, but you'll find that it maybe is a little bit easier to deal with if we use the rationalized version. Cosine of 30, adjacent over hypotenuse, again at the 30-degree angle, that gives me square root of 3 over 2. Sine of 45, opposite over hypotenuse, 1 over square root of 2, or again, square root of 2 over 2. And the sine of 30, opposite over hypotenuse, is going to give me 1/2. So now I'm just going to do some arithmetic to put this together. We've got the square root of 6 over 4 plus the square root of 2 over 4. And all together, I can write that as one fraction, square root of 6 plus square root of 2 divided by 4. Remember, the square root of 6 and the square root of 2 cannot be combined together since they're added, but I can put them together in the numerator. So they don't combine together within their square roots, but I will combine my numerator into one fraction here. And that'll be our final answer for example number 1. Now, as we move on to the next examples, what you're going to find is there's really a limited number of problems where we can rewrite it in such a way, right? Because we would have to have something that adds or subtracts from one of our special triangles. So there's not like, we don't have an infinite number of possibilities of angles that we can rewrite. And so a lot of your answers are going to look similar to one another because I really can only use the unit circle answers, 1, -1, 1, 0, and then also the answers that come from these special triangles. So you're not going to have something that's like the square root of 7, because that wouldn't be something that would occur from the values that I have listed here. Let's try it again for example number 2, finding the sine of 255. Again, I would encourage you to think of what adds or subtracts to 255. You can pause this video. What adds or subtracts to 255 from the special triangles or something that is a reference angle from one of the special triangles. And so the one that I'm going to use is, I'm going to say that 255 comes from 210 degrees and 45 degrees. That adds up to 255. Again, there's a lot of other options, so if you picked something different, that would be fine as long as it adds or subtracts to 255 degrees. 210 degrees is in our third quadrant. It has a reference angle of 30 degrees, so we can definitely use that angle, and we'll know that it has that reference angle here. And then sine of 45 still in our first quadrant. And so I'm just going to redraw that 45, 45, 90 triangle. And like I said, you probably have it already on your paper or in your homework. You're going to just have that on the side so that you don't need to rewrite that each time. All right, let's expand this using our formula. We've got the sine of two things added. So I'm using the top line here, sine x cosine y plus cosine x sine y. So we're going to have the sine of 210 cosine of 45 plus the cosine of 210 and the sine of 45. All right. Now we'll evaluate each one. Sine of 210, based on this 30-degree angle, again, you're going to have 1 square root of 3 and 2. You might be able to just use your special triangle with the 30, 60, or the 90. You might also look at this picture where you can see the direction to see that the sine in this third quadrant is going to turn out to be negative. Sine of 210 is actually going to be a negative 1/2 based on the side lengths here. You also know that third quadrant has a negative sine value. Cosine of 45 from our triangle, that's 1 over square root of 2, or in other words, square root of 2 over 2. Cosine of 210 is again looking at that 30-degree reference angle in quadrant number 3. That's going to be negative square root of 3 over 2. We know tangent is positive in this third quadrant. That means we also know the cosine is going to be negative there. Sine of 45, square root of 2 over 2. Start combining all of that together. We get negative square root of 2 over 4. We get a negative square root of 6 over 4. And we can combine that together to one fraction, negative square root of 2 minus square root of 6, all divided by 4. That's a great answer right there. Sometimes people like to check their work, or they're wondering, how in a test would I know if I have done this right? You could type in this quantity into your calculator, and then you could also type in the sine of 255 degrees, and you could check to ensure that you're going to get the same decimal for each one when you type them in. So that's one good way to double check that you have the right answer there. Another thing that I want to point out in terms of how you could write the answer, since they're both negative, sometimes you're going to see your textbook factor out that negative square root of 2 plus square root of 6. So if you see a positive sign in there when you're checking your answers, don't panic about that. They may have just factored out the negative and pulled that out front. So we just want you to be aware of that. All right, the tangent identities. So again, if you're writing these on the back of your green sheet, this would be number 3 for the tangent of x plus y and x minus y. We can group those together into one identity, tangent of x plus or minus y. Notice that the sign is the same in the numerator as it was in the parenthesis. Your sign is the opposite in the denominator as it was in the parentheses. So we get tangent x plus or minus tangent of y, and then we're going to divide that by 1 minus or plus, because it's going to be the opposite, tangent of x, tangent of y. Now those two things are multiplied together. So I'm not going to do a tangent example, but that goes in the same process as what you've done for the sine and cosine. Now, just to make you aware, another option, of course, is our tangent identity. We know that the tangent using the quotient identity is sine over cosine. And so what we could also do is we could say that the tangent of x plus or minus y is equal to the sine of x plus or minus y divided by the cosine of x plus or minus y. So those addition and subtraction identities work the same for our quotient identities, combining those two together. So if it happens that you already know the sine and the cosine of something that's being added or subtracted, then we can figure out the tangent pretty quickly from there. One last example for us is verifying. Now we're going to verify an identity that has addition in it. So remember, I can't distribute that cosine through, but as I verify, it means that I'm going to make one side look like the other. And so we start with the more complicated side. So in this case, that's the left-hand side. And I want to turn the left-hand side, cosine of pi over 2 plus x, into negative sine. And the way that I'm going to do that, of course, is to use our sum and difference identity. So I start by writing down the side that we're beginning with. So that's the cosine of pi over 2 plus x. And now I'm going to use the sum and difference identity with the cosine. So that gives me cosine of pi over 2 times the cosine of x minus the sine of pi over 2 times the sine of x. Now, as we were verifying, we said one thing that we want to do is we want to say, well, what do we want our final answer to be? What are we looking for? And in this case, it looks like we're looking for negative sine as our final answer. So if I was guessing and just kind of thinking ahead to what's supposed to happen here, I don't want any cosines in my final answer. So I'm really hoping that these cosines right here are going to disappear, right? If I want those cosines to disappear, the question is, how do I make that happen, or is that going to happen on its own? Let's evaluate the cosine of pi over 2. The cosine of pi over 2, or 90 degrees, is 0. Oops, change that to a color you can read. So we get 0 here times the cosine. The sine of pi over 2, what's the sine of 90? That's a 1 times the sine. Ah, look at that. We wanted the cosines to disappear, and lo and behold, the cosine of 90 is 0. That knocks out this whole term. 1 times the sine is just the sine, and we have a subtraction, so that's like a negative sign. And look at that. We're already to our final answer. We proved, using the sum and difference identities, that the cosine of pi over 2 plus x is equal to the sine of x.